The first thing that I want you to do today is we're going to review a little bit from last time. You're going to pick up a maze from my desk or from the substitute, and you're going to complete both sides of it. What you're going to see if we zoom in is a bunch of rational exponent problems, or the other side. They're given to you as radicals, and you're going to put it into the other form. Whichever one you start on, it doesn't matter. Make sure you start at the one that says start on either one. So like here you'd start at x to the 1/2, and you're going to rewrite it, and it's going to tell you which path to go. So like we know x to the 1/2 is the square root of x, so we would go this way and now complete this next problem. Okay, go through, and it should all the way lead you to the end over here eventually. So you're going to map through the maze, and again, do both sides. So you're also going to try this other maze and start reading here, rewrite them as exponents, and get all the way over here to the end. Go ahead and pause the video. Give yourself time to do that, 10, 15, 20 minutes, whatever you need, and then unpause it, and I'll show you the answers on the next slide. Now that you've gone through the video, check your answers here and see how you did. This should have been your paths all the way through. Pause it, feel free to talk through anything that you got wrong or any parts you had questions on, and then continue the notes. If there are homework questions that you have, feel free to take some time to stop and talk about those together and work through them as a group. And then if you have any additional questions, come to see me when I'm back in school. Today we're going to learn about what's called complex numbers. And this is going to find a way for us to deal with some problems that in the past you have historically stopped halfway through. As we go through these notes, feel free to pause it to give yourself time to write things down. I will not stop as I go through, but again, just pause the video so that you can write down what's on each slide. The first thing we have to talk about is what's called imaginary numbers. And imaginary numbers occur when there is a negative under a square root. Mathematicians ran into a problem where you'd get a negative under a square root and you couldn't finish the problem. And there's different applications in a lot of higher level math that needs you to be able to go past this spot where you got a negative under the square root. To overcome this, we came up with a notation that will help us to deal with this issue. And what we decided is we would let the square root of -1 equal I. And there are certain times in math where we just decide something so we can keep going. So this is one of those things. Where this will come into play, say you had the square root of -64. Before today, you would have had to stop. You can't simplify this problem. You would just be done. However, using this definition right here, that square root of -1 equals I, what I can do is say, okay, since there's a negative under this radical, it really comes out as an I. So I have I times the square root of 64. And then we can square root this 64 like normal. We know that that is 8. So the answer for the square root of -64 is 8I. Basically, whenever you have a negative under that square root, you know you will have an I in your answer. We don't have to have perfect squares to be able to do this. You could do it. Say I gave you square root of -12. Again, we can pull the negative out as an I. And then think about how 12 breaks down. 12 is 4 times 3. So this would be 2I root 3. So we can now simplify radicals that have a negative under them. You will just need to make sure that you put an I in your answer. This is the part that can get a little hairy, so make sure if you need to come see me to go over this or ask a different math teacher some questions about this today, feel free to. Because this can be the part that gets a little more theoretical instead of just being straightforward math like you may be used to. What we found out is that the values of i's go through a certain pattern, and they let us simplify our problems more thoroughly as long as we can recognize what that pattern was. So first off, if we have an I in a problem, we're always just going to leave it as an I. We can't simplify that any further. Like on the last one, you would just have 8I and you wouldn't do anything. But if I is raised to different powers, there are different things we can do with this. So for example, if I was squared. When you square something, what we got to talk about is what that does if you have a radical. So for example, just off to the side, if I had the square root of 5 squared. Well, going through the work, we know that 5 squared is 25, and we know the square root of 25 is 5. But what I want you to see is that this square root and this squared really just cancel out, and your answer is just the 5 that we had originally. If we apply this here, we know that I is the square root of -1. So what I'm doing is the square root of -1 squared. Following what we talked about here, where the square root and the squared really just cancel out and give you what's under it, the answer for I squared is -1. Yes, I know that you could technically square the -1 first, tell me +1, and then you would square root +1 and get +1. But this is how imaginary numbers were defined. We need it to be such that if you square I, your answer is -1. So that's very, very important. So here, we're focusing more on the fact that the squared and the square root cancel out than on doing the actual operation of squaring this -1 and square rooting it. Okay, so focus on the fact that the squared root and the squared undo each other, and your answer is -1. Okay, so where this will come into handy later, if I ever have I squared in a problem, I can get rid of that I entirely, and that's why we like this. If I keep going, I cubed, and I'm going to split this apart so we can kind of figure out what this would be. What I want you to think about, I cubed is the same exact thing as I squared times 1i, because if you do 2 plus the 1, you get 3. And then what we can do, okay, I squared, we already said was -1, so I'm going to replace that. And then my answer is just -I when I do that multiplication. So if I ever have I cubed, I don't need to have an exponent anymore. I'm just going to write -I. One thing you may have noticed, and I should have mentioned before, when I write my i's for my imaginaries, I always curl them a little bit, and the main reason for that is so I don't get them confused with a 1. So whether you make sure you have a really big dot above it or you curl it, just make sure you can tell the difference between your I and a 1. Okay, if I keep going, I to the 4th. Again, if I rewrite it, and you can rewrite this multiple ways, but I'm going to do I squared times I squared. Again, 4 is 2 plus 2, so this works. We can add our exponents together, so I haven't changed it. But I know both of those I squareds are -1. And then when I do that multiplication, -1 times -1 is a +1. These first 4 are the super important ones, so if you need to pause it and re-listen to where I got any of those values from, feel free. And I'm going to show you what happens after this. If I do I to the 5th, if I split it apart, you can do this multiple ways, but I could rewrite it as, say, I to the 4th times I. And I know that I to the 4th is really just 1, so this is 1 times I, or just I. If I do I to the 6th, again, I'm just going to rewrite it. Maybe I take this as I to the 5th, or no. We could do I to the 5th. I to the 5th times I. Well, we just said I to the 5th was just I. So this I to the 6th is I times I, or I squared, which again, before we know, is just -1. What I want you to see is this is starting to repeat itself. I to the 5th was the same as regular I. Oopsies. Forgot my squared there. I to the 6th ended up being the same as I squared, or just -1. I to the 7th is going to give me the same as I cubed, which is -I, and so on. It's going to keep going through this pattern. What will always be is wherever in the terms of dividing by 4 rotation you're at. So say, for example, I wanted to calculate I to the 25th. What I would do, 25 divided by 4 gives me 6 with a remainder of 1. Okay, that means it went 6 times through the full rotation here, and then it went 1 more. Okay, on that 1 more, this really tells me what my exponent is. So I to the 25th is the same as I to the 1st power. what this lets you do, again, is approximate any value of I anywhere along the way and bring it back down to something much nicer. So for example, if I just make one up, I to the 15th, 15 divided by 4, and goes in 3 times with a remainder of 2. And so this 2, again, tells me it's the same as I squared, which is just -1. So what I want you to see, the ones that are crucial to know are these first 4. And if it will help you out to write a smaller list, okay, what I would do is make in your notes, you always keep I being I. You let I squared be -1. You let I cubed be -I. And I to the 4th be 1. This is going to be super important for you. Knowing that it will rotate then through all the values is the second thing I would make sure you know, so that you could find me any value of I that you want. What the rest of the notes are is talking about complex numbers and how we do operations with those. Complex numbers are numbers of the form a plus bi, where a is some real number and b is an imaginary component to your value, your bi is. So this could be anything. For example, it could be 2 plus 3i. It could be 4 over 7 plus -8 over 3i. Okay, those could be fractions, they can be whole numbers, but you're going to have a real number portion and an imaginary portion on your number. We can do operations with these complex numbers the same way we do operations with about anything else in this class, and so we're going to practice that a little bit. And your operations are really just going to be addition, subtraction, multiplication, and division. The same thing we've been doing with all of our radicals. We're just now going to do them with complex numbers. For example, we have one like this. With this, what I want you to notice is whether or not those parentheses actually matter. I don't have any multiplication outside of our coefficients multiplied with the I value, and so none of these parentheses are actually important in this, but I want you to see that so that you don't accidentally do it wrong when you get to your test or your quiz or anything. What we're going to do here is the same thing you would do if these I's were X's. So you're basically thinking of it as combining like terms. So my answer here is -4 plus 4 plus 2 plus 8 is 14, so 14i. Done. Your answer has to be in the correct form for a complex number, so this is an a plus bi, and we are good to go. For one like this, I have 3 different things multiplied together, the 2, the -3i, and this binomial. When you are multiplying, remember your order does not matter. You can multiply any 2 together at a time and then multiply that answer to the third. So for example, what I would do first is I would do 2 times -3i and get -6i. And then after I've done that, you're going to distribute through. So I have -42i minus 42i squared. But this is not in the correct form. It needs to be a plus bi, which is not in that form yet. And the issue I have is this I squared. But what we talked about on that previous slide and why it's so important is that I squared is the same as -1. So this -42 is really just multiplied by -1, which means I can do -42 times -1 is now plus 42. And then my minus 42i stays the same. Now this is in the correct form. So because we had an I squared, we replaced it with what it equals on that previous slide of I squared equals -1. Doing this multiplication gives me the 42, and now it's in the correct form. Go ahead and give this one a try, and then unpause it and listen to the explanation. On this one, I'm going to start by distributing. So I have 28 plus 7i. And then I'm going to do 3i times 5 is plus 15i. And 3i times negative 2i is negative 6i squared. Again, my end goal is to have it in the form a plus bi. So I need to put together my like terms as well as get rid of any I that's raised to a power greater than 1. So this negative 6i squared needs to be negative 6 times negative 1, which is the same as just adding 6. Okay, and then I can look at my like terms. I have 28 plus 6 is going to be 34. And 7 plus 15 gives me plus 22i. Okay, looking at division, we're going to have to do this much the same way we were dealing with division of other radicals. So I'm going to make up a problem that's similar off to the side. This is nothing to do with the problem over here, but it will show us how we will solve this problem. So what I want you to think about is how you would solve a problem like this. Okay, if you have a radical in the denominator, what we talked about is you can't leave it like that. You have to go through and force that radical to be a perfect square. And so what we did before is we multiplied by that radical on top and bottom. And our answer then was 2 root 3 over the square root of 9, and we were able to simplify that and get 2 root 3 over 3. This problem is really no different than the one we have right here in theory, because our issue is still that we have a radical in the denominator. This I is a radical in the denominator. It is not as obvious to be a radical, but based on our definition, that's the square root of negative 1 in the denominator, and so we cannot leave that as such. What we have to do, just like we did over here, is multiply by that radical on top and on bottom. But now my radical is just an I. When I do this, I'm going to distribute it through on top, so it's 4i minus I squared over 10i squared. When we go to simplify, both of these I squareds are really a negative 1. And what that does for me is it gets rid of the radical, or the I, in my denominator because I forced it to be a perfect square. So now instead of having an I in the denominator, it's just a 10, or a negative 10. We do need it to be in our correct form, the a plus bi. So I'm going to pull this apart so that it's two different numbers. When you're doing this, what you need to remember is that both the 4 and the 1 are divided by this negative 10. So I'm going to pull it apart as the 4i over negative 10 and the 1 over negative 10. And we're going to be able to simplify both of these, or each of these. I'm not super particular about which order you write these in. I will keep writing it in a plus bi, so I'm going to put the a first. But if you flip it, that's not a problem. So I'm going to put the 1 over negative 10 first. What I do know is that I can just write that as negative 1/10, because the negative doesn't matter if it's top or bottom. And then looking at this one, 4 over negative 10 can simplify a 2 out of each of those. So this is minus 2 over 5i. That is my final answer. For the last example, we're going to do one where there is a binomial in the denominator, so having this addition or subtraction in the denominator. And again, it's similar to if this was a radical with addition or subtraction somewhere. How we did this problem, that again has nothing to do with this one, it's just to make sure to pull you back your previous knowledge. What we did over here is we multiplied by the conjugate, so we did root 2 minus 1 instead of root 2 plus 1. And then we multiplied or FOILed everything through, and this denominator ends up not having any radicals in it when it's done, as long as you do it correctly. For this problem, you're still going to multiply by the conjugate, so I'm going to change the middle sign, so it's going to be negative 3 minus 2i. And then we're going to FOIL this all the way out. Take a second and try to FOIL it, and then play the video to make sure you did it correctly. On top, you should get 21 plus 14i minus 12i minus 8i squared over 9 plus 6i minus 6i minus 4i squared. Once you've done all of that, you're going to go through and be able to simplify your I squareds. So both of these are really a -1, so I'm going to do -8 times -1, now I'm adding 8. And -4 times -1, and now I'm adding 4. When you go through and simplify, I can do 21 plus 8 is 29. 14 minus 12 gives me plus 2i. Over, these 6 i's cancel, which is important. And then we just have 9 plus 4 is 13. Again, I want your answer in the form a plus bi, so I'm going to split my fraction. I have 29 over 13 plus 2 over 13i. Neither of those can simplify, so this is my final answer.